Welcome to this class, and it's very excited to have all of you together to learn sheet metal stuff. Firstly, we'll do some self-introduction. I am Nina, then working as an experienced designer for Inventor and working for Autodesk for more than 10 years. I worked for several projects like modeling, assembly, tooling, beam content, and sheet metal. And River is a co-speaker, and he is an expert for Inventor, and also worked for many projects like tube and pipe, and frame generator, and sheet metal. So he contributed a lot of tips and experience for this slide and for this class. So both of us has a background for mechanical design. So we went to Autodesk and grew up with Autodesk and learn a lot from our great customers, and you are part of them. So firstly, let me say thank you for all of you for the continuous support and great comments. And then let's go back to our topic, sheet metal. Before we start the class, I want to ask a question. So how many have you using sheet metal today in Inventor? Wow, cool. Okay. For the summary for this class, the title for this class is to learn top-down design with multi-body. And during this class, we will comb the whole sheet metal system, since everything in the system will help you on the top-down design. So this is the objectives for this class. Firstly, we will learn that how to set up and manage sheet metal rules. And the second is how to make use of sheet metal features. So as we know that although sheet metal have existing for many years, but some customers or some engineers are still using modeling tools to create sheet metal feature. So let's go through some good tips for these features and to ease your work. And the second one is go to make top-down design with sheet metal. And the fourth one that we need to pay attention to is get tips to ease your work. So these are great tips. So if you pay attention to these tips, that you will get a chance to get a gift in the final of the class. And finally, I will tell you that where to find us during the AU time. So most of us know that sheet metal works for industrial machinery and for these mechatronics enclosure or cabinets or even transportation truck. A lot of machine stuff, metal stuff, but also sheet metal can working for this paper stuff, and it has a packing box, and also we can make this stuff with sheet metal, and we'll make a simple VR glasses. So we will show this model in this class in the top-down design section. So that's the definition on when do you need to use sheet metal for the final single-piece part for manufacturing. So pay attention to my description as a single-piece part for manufacturing. So you have a uniform material, need to have uniform thickness, and also it needs some work for bend and folded. So then if you meet these requirements, and you can choose to use sheet metal. But if you have any definition beyond these requirements, and we can talk more offline of the class. Yeah. So who used sheet metal from R3? Whoa, thank you so much. So that's a history for Inventor sheet metal. So it has been 16 years old for sheet metal, and we just keep investment on sheet metal design, and for some key milestones like R6, we provided a punch tool, and for 2010, then we have a refold and fold provided, And most important, from 2016, we provided multi-body in Inventor. Then it gives opportunities for you to make the quick top-down design. And in 2018, so I cannot talk too much about 2018 since for confidential problem, but we welcome you to join us in beta forum and for the new functionality, validation, review, and provide comments. So we have some engineers in answer bar, and you can find us if you want to join. Okay, so by looking at the sheet metal system as a tree, that it will be easy to understand that how sheet metal works. So, we call the sheet metal roots. It behaves like the root of the tree. It supplies food and waters to the branches and to the leaves. So everything can live. For solids, it becomes like main branches. So from 2016, Inventor has multi-body. So who already used 2016 now? Oh, cool. So I start using multi-body. Okay, cool. So it's a good starting for multi-body support in 2016. And these features behave like leaves. So these features doesn't only mean sheet metal features, it also means all general modeling features. Since it's powerful tools and you can use them anywhere, just follow the sheet metal rule. So a little special one is the override. Overriding behavior in Inventor. It looks, we can take them as the weather. It's like the rain, like the snow or sun or wind, and it will impact the growth of the tree. By default, that you always get the rules from the sheet metal rule. That's like the unfold rule, bend creation and corner creation. But in each feature, you have the opportunity to customize these rules separately. So that's the overriding behavior. Okay. So let's start with the root. It's the sheet metal rules. So since most of you have the sheet metal experience, so we can go through this very quickly. So we will learn that how to set up sheet metal rules and how to understand and set up and folder rules. And finally, we will see how to share the rules with team once you set up all this stuff. So you can access the style and standard library from this command, style editor. Also, you can access this from the sheet metal defaults dialog. There is a little icon that can help you to access this dialog. So that's the start point for sheet metal design. And there are two main parts. The first one is the sheet metal rule, and the second one is unfold rule. So for sheet metal rules, there are three main parts. It's for the sheet plate, for the bend, and for the corner. So for the sheet, that there are two essential definitions you need to finish. One is the material, another one is the thickness. So this material drop-down list that is shared in Inventor anywhere. So you can customize your material and access it from here. Oops. So for bend, the most important thing is to define the relief shape and the bend radius and the bend transition. So there are three types of relief types in Inventor. It's a round, tear, and straight. So for corner, it's similar with bend that you need to define the relief type and the relief parameters. So we come to unfold rule. So unfold rule is very important for what? It's for to come up with the material length before you go to bend it, before you go to manufacturing it. So Inventor provided three ways to calculate the developed length for the whole material. So the most basic one is the KFactor. So KFactor is the factor to define the position for the neutral surface. So from this image, we can find that KFactor equals gamma divided mu. So KFactor is a value from 0 to 1. It means the material from soft to hard. And the typical range for the KFactor is from 0.3 to 0.5. So usually you decide it based on your material. So with this equation that the inventor calculated the material length before you go to bending. So from this LBA is the bend allowance. It's the length for the neutral surface arc length. So with L equals L1 plus LBA and plus L1, it's the final developed length for the whole material. So from this simple example, we can check that it's exactly the same value after flat pattern, and the value is equal with the formula. So just trust the inventor. And bend table usually got from your supplier or from your manufacturer that you can import existing TXT file that in this bend table, and it defines a length correction value that specified bend radius and bend angle. So internal, we are using this equation to calculate the total length. So it's much like the equation for deduction. Later, we will see this. So this is the last added one in Inventor that to calculate the length by the equation. So we have 4 types of equation: bend allowance, compensation, deduction, and variable KFactors. So you can come from the image that the annotation for L1 and L2 is a little different. But it doesn't matter, since you decide which equation to use is based on your manufacturing condition, your material. So in each equation that you have the opportunity to define the formula and specify the bend angle that you can edit each of one or add your own ones in the specific range. Okay, so after you set up all rules, all styles, and then you want to share with the team, so you can save this file as a template, and then finally you can use this template directly, and everyone can use it. Okay, so here is a quick demo in Inventor. So this file that is I created before the class, and now this is another access point to access the style and the standard library. So here I created many sheet metal rules, but you have your own name, file name definition rule. So my rule is much simple with material and with a thickness, but your rule must be much more professional. So most important thing is that we need to define the thickness, define the material, and unfold rule is embedded in the sheet metal rule definition. So once you can edit the unfold rule by click this button, and it will go to the unfold rule for this sheet metal rule. So also you can change back and change another unfold rule. So after you finish that, just save as a template. And in the template file location. So, but I don't need to do that since I created one called AU 2016. So next time when I new a file that is a sheet metal, the new template will be shown here. Okay. So come back to the slides. Now we will go to the sheet metal features. So it's a leaves for the sheet metal system. So what we will learn that in this section, we will go through some base features that how to create the sheet metal body initially. And the secondary features to continue the sheet metal design based on base features. And also another popular workflow is to convert sheet metal from a standard part and to extract sheet metal plate from existing solids. So with all these feature tools, that you get the chance to make a multi-body in Inventor sheet metal. So flat pattern is another important area we need to mention in this section. So there are 4 main tools in Inventor to create a sheet metal solid. So I mentioned this because from 2016, that we provide multiple body support. And for these 4 features, there are options to say I want to a new body, or I want to join with existing bodies. So it's a face, contour flange, contour roll, and a lofted flange. So I add extrude here. It doesn't mean it's not important, since it's a general modeling tool, and you can use extrude anytime you want to use. But just extrude the required thickness. So with these base features, that you have the opportunity to create the solids. So in this example, that there are 9 solids in this stapler, and each of the solid is started with a base feature. So take face as a simple example, that you can click the first profile to create a new solid. And for second profile, that you can choose, say, I want to join it with the existing solid. And for the third profile, you say, I want to new a solid. So after doing this, there will be two solids existing in this sheet metal part. So with the contour flange, so it's like you must have a sketch profile, and you use this sketch profile and to sweep it through edges, or sweep it with a distance to be normal to this sketch profile. The most important thing is that during the creation, if you have multiple edges selected, that auto mattering will be created automatically. So it will save many steps for you if you just use general modeling tools to do this work. Okay, here it comes the first tip. So for lofted flange, that it's you can loft to close the profile, and it can be created successfully. But if we only with close the profile, that you cannot do flat pattern. So before you do flat pattern, you need to create a rib that to make it happen. So for contour roll, that the tip is that you must create an open profile for this command to make it work. So here is a very simple demo to connect all these base features. So I prepared some sketches in this model to save some time. So firstly, I created a sketch for face. So face is already created, that with a new solid selected. For the second one, I want to use the contour flange. So this profile is selected automatically. So now I have the chance to say I want to create the contour flange along these edges. So I can pick these 2 edges, or I can just pick a loop. Then I can create a contour flange in the same time. And here is the option to say, do you want to apply auto mattering? That by default it's checked on. So if we check it off, that it's not required, right? So we can create this one, And here is a chance to say I want to create is by new a solid, or by join the existing solid. So let's pick again. Sorry. And now we go to say I want to create a lofted flange, and I loft from this sketch to this line. And here is some options to say that the forming methods for the lofted flange. Press break is checked on by default. Also, there is another die formed, so you can choose based on your manufacturing needs. So finally, that we got a chance to create a contour rule. So for this contour rule, that in this sketch preparation, sorry, that it's tangent, right? So you can connect these two features together. Okay, so this is a quick through for base features, but I want to mention one is for contour flange, that actually they are very powerful west extend tools that you can use edges. Also, you can use the west values to control the extents for this flange. So we will mention it later, since this functionality is shared by many commands like flange, like ham. Okay, so come back to the slides. So for secondary features, that there are a lot of secondary features, but we will not go through everyone since the time limited. So we just provide some tips for many of them. So flange is the most often used secondary features to continue the sheet metal design. So from this simple case, you will find it's two solids. So when you pick edges in flange, that it's supported to pick edges across the solids. So you can pick edges from different solids. So autometering will be created automatically. So that's powerful. And also, besides flange, for corner seam, for cut and bend, it has the same functionality that you all support to pick edges to cross solids. But the request is these solids must have the same sheet metal rule. So here is a tips for flange, that sometimes that you want to create a flange that to be parallel with the side face, but the angle is not easy to find if you flange from the top edge. So it's easy for you. Just say you need to create the angle as a parameter, and then you link this parameter in the flange angle. So anytime you change this angle, that the flange will be updated associatively. So I can show this model. For this model, it's easier to find this angle, since this angle is created from the cut feature, cut sketch. So this angle is created. So in flange, it just link that this to D16. So sometimes we use these methods. If you want to link parameters from other features, you just click show dimension, And so for example, I want to link some parameters from this feature. I just click this feature, and I can pick dimension from the screen directly. So when we change this, this parameter to 60, so this flange will be updated associatively. So for other cases that if there is not angle, if there is not an angle, existing angle to make use of, that sometimes we will create a work plane to be parallel with this face, and then create a profile on this work plane, and use face command other than flange to create this feature. Okay. So next is cut. So it happens often that the cut is not normal to the target faces. So once you meet this situation that you are required to check on the cut normal. So when it's not normal, you check on cut normal. So it's very easy to remember.
Is there any way to set that as a default option?
Yes, it's default not.
Yeah, no. So I think the default option is the cut, like the extrude cut. So
I didn't know if there was any way in the preferences that you could go in, because I have users that used to do that all the time and then they crash.
Oh, I'm sorry for that. Okay. So I think we can record this problem, and you can find us in answer bar when you have time, and we can practice it. Okay, thank you.
So from my perspective, I think this is not a general problem. So maybe we can submit the CR report to us and provide the data set, so we can have the future investigation and provide feedback to you. So if you have any question or problem, you can go to the answer bar. We can have a more offline communication. Okay, thank you.
Okay. Okay.
Isn't that setting persistent in the document settings and not in the Digitecno file?
So you mean if the last setting is saved? I guess it is.
I think it is. So
Yeah.
you should be able to select the cut normal option.
Yeah.
And then save it in the sheet metal template. So you can make that selection.
Oh, got it. Yeah, yeah. I think it's a good idea. Yeah. It's a workaround, but we will see if it's possible to add options somewhere, since we have a bunch of options already. So people hate options, so we need to consider that, whether or not we need it, or just save last settings in this command. So this is another tips for cart, that sometimes you need a cart on the road surface. So if you just cart in this situation, that you always will be filled on flat pattern or fulfilled for the manufacturer. So the recommended workflow is that if you already get this step and you need unfold it to be a planar. And then you create a cart and then refold it back. And now you will get a beautiful result for the cut in the flat pattern. So for punch, you need to prepare a 2D sketch firstly with a center mark, with center points prepared. And then go to click punch tool, and you will be navigated to the punch library. We provided some existing simple punch tools there, and if it's qualified that and you can need it, and you can just put it on your sketch point, and like this, the dinner plate, and it's easily to create it. But if you don't have a punch, you don't have the punch in the library that you want to need, that how to create it. It's not usually, it's required that you create with iFeature that we have 5 features supported in iFeature creation. So it's cut, extrude, revolve, sweep, and fillet. So you cannot use other features, or else that they will not be recognized by iFeature creation, by iFeature publisher. So for this example, that we create this punch feature, and with many revolve fillets, and then we go to the extract iFeature. It's a publish. You can publish this punch iFeature to be in the punch library, and then you can locate it in this plate easily. So let's have a quick demo. So this is a simple case that we create. Firstly, there's a faceplate, and then we create a sketch for this feature. And firstly, we revolve the first step, and then we get the second step. So we get this window seat in 2 steps. And now I go to the Manage tab and find Extract iFeature. So for punch tools that you need to check on this sheet metal punch iFeature, then you can choose these 2 steps and say this iFeature only includes these 2 steps. And now you can specify the sketch, and now you can save it to the punch tool. And you can save it in the punch library. This is already created one. So to make it simple, we just click center point, but actually you need to make it seriously. So click punch tool, and I can get a large icon size. So I can pick this iFeature to say I want to put it here. So when you see the color becomes this one, it means that this shape cannot work for this plate. It often happens that when the thickness doesn't fit the original one. So you need to change the size to be bigger. And after you refresh and click it, and you can put this punch tool in this plate successfully.
Since we're talking about iFeatures,
Okay.
is there a way to include parameters in punch ID so that when you go to detail it on a drawing, you can actually, like for a slot, you can actually have it call out the length and the width of that slot?
Okay. So
currently, so punch ID, I think we can use the punch note. We can add the ID to the punch note. So I think you have used the punch note in drawing, so you can add the punch ID within the punch note.
Right, but if we have a slot that can change length and width depending on what you enter in for your options there, can you bring that information into that punch ID to display it on your drawing?
So you want to display the punch parameter together with the punch ID. Okay.
Yeah.
Okay. Okay. Yeah, we'll take notes. Thank you. Yeah. Okay. So then it's a flat pattern. So Inventor from the file structure will have 2 folders to represent two status for sheet metal. So one is the unfolded model, and the other one is the flat pattern. So usually we use flat pattern for two purposes. The first one is to validate, to prove it's a validated design. So if the sheet metal can be flat patterned, it means the sheet metal design is good. But if it cannot, then you need to recheck your design to make it work. So only one exception is the iFeature. It's just a punch that for iFeature that it accept cut-through features, that for other punch features that they cannot be flat patterned. But it doesn't matter. It just have different representation options for you to choose, that you can only display the sketch point, center point, or you can display the sketch, or just this unflat patterned form in the flat pattern status. And the other purpose is serve for drawing and manufacturing. So like you mentioned that you want to create the punch table, punch notes with ID or with parameters. That's one request. And the most popular is the bin table and the bin notes, and as listed in this image. So here is the tips for flat pattern. So usually when we do modeling in folded model, that the flat pattern will be updated at the same time. But when your model becomes complex, you have maybe hundreds of features, or you use iLogic to drive this complex model, and or you have hundreds of pattern instance, that then it will make the updates to be slow, to make the flat pattern updates to be slow. So there is an option called the defer update, and you can check it on. And when you check it on, that the status, the icon sign will tell you that it needs to be updated, but it's hold on. So you can do it later.
Yeah, just one comment. Okay. So if you open the sheet metal part, you can select this option from open file data. So we have a complex sheet metal part with flat pattern. Yeah. So if we can take on this option in open file data and open. So yeah. Maybe the performance should be better.
Okay, good comments. So it's easy if you just open a large sheet metal design. So you can make it quicker from the very beginning. So this is a popular workflow that, but this image showed a workflow that you get some sheet metal metadata from a non-uniform solid, right? So this is a solid, and I want to get a sheet metal design based on this solid. So usually there are two general tools to use to extract the sheet plate from a solid. That one is the shell, and the other one is the seeking and offset. So it's popular used. So when you click the convert to sheet metal from standard part, so here is a tip that many people may ignore this tooltip, that it says it side select a base face, but since the information is not complete, so it's easily to be ignored. But it means that you select a base face, and the inventor will get the thickness value directly. So you pick a face, and we get the thickness, and we'll fill in this thickness. We'll fill in the sheet metal default thickness override value directly. And then for the all downstream features, we'll follow this thickness definition. So we go to a quick demo on how to make it. So for this workflow, it happens that I extract the sheet information before go to convert sheet metal. So in this demo, I will show that a quick one. It's like how to use a shell to do it. So if I use 1.1 inch for this shell creation, and then when I go to convert to sheet metal, here is a cursor. You will see select a base face. So I can pick this face. I think I get a defect. Okay, sorry for that.
So because the cursor, if you select the, maybe sometimes though, it's better for us to select the most biggest planar face to detect the thickness. So you can see maybe Nina select a position close to the corner. So maybe it's something wrong here.
Yeah, I did a good demo for a bad case. So so I do it again. So convert to sheet metal and pick this big face. Oh, sorry. I did it. Okay. Whoa, get a tip. Thank you.
So what if you have sheet metal styles that are defined, and the thickness, like the thickness you selected is one of those thicknesses in the style?
Yeah.
I mean, in my mind, you wouldn't want to change the active style. The default style would be that thickness. You want a window to pop up and show you these are the styles that you have in your library that match that thickness
Sure.
you want to use.
Sure.
Because you want to use the correct style instead of default, because that's what updates your correct KFactor and material for that part.
Yeah. So we will answer this question.
Okay. So I think I got your question. Actually, you have defined multiple shipment rules in the template, right? So if you share the slant part and want to automatically match the rule you defined when convert part to sheet metal, right? Okay, so if you have defined the sheet metal rule or styles in the template, when you share the body, share the part, you can use the thickness from your defined rule as the distance.
Yeah.
So because this information is stored in the part, so you can use the thickness directly as the distance.
Yeah. So like River answered that when you convert to sheet metal, and you can use anything from the sheet metal rule. So I just typed the thickness in this dialog, and it will use the thickness from the sheet metal rule directly. Yeah.
Can I add something just to clear some light on that?
Sure.
I was concerned about it, but also I spent a lot of time testing it. And so let's say you've got a quarter-inch plate, and you've got 5 of those with that distance defined in your sheet metal style. It basically will grab the first one on the list, and it gives you the opportunity to switch to one of the other ones as well. So you can override or you can tell, what one you want to use. Otherwise, the first one is in your sheet metal style, which matches that size. It works really well.
Yeah, that's right.
Thank you. So when you're talking about this, I'm just cannot stop me to to share something about the new features, but it's something related. So if you are really interested in this thickness definition for multi-body, that I just say you are encouraged to involve us in the beta forum to test with the new tool. Okay. So next, that to make the demo simple, so we just say I want to create some opening, create a rip for these edges. And then go to bend, say to make it to be a sheet metal part. Then it's a sheet metal now, and to validate it if it's qualified, we create a fed pattern, and it's successfully. So this one is good demo. Okay. Okay, so this is the main purpose for this class is to introduce top-down design. So we went through the sheet metal rules and the sheet metal features, and we know the capability, the basic capability for Inventor in feature level. That for features that you can create multi-body, these just the functionalities. But how to make the design, it's a little different. So it needs some method and methodology, and to connect these tools together and to make your work easier. So firstly, we want to summarize the key characteristics for top-down design. So it's a method, and it has some key factors, like it's in context to design. So each design is happened just in the same context. So the second one is it support for collaboration. Since everyone shares the same picture, so it works for a team and to share the work. And the third one is it's high efficiency on design change. So since usually top-down design have a skeleton model as a basic, so any changes happened around the key, around the skeleton model, that it will be updated, go to the downstream directly. And the last one is a quick response for cost control. Since the design change is easy, so it's much easier to make quick changes based on the cost. So the image side, the architecture world, right? For architecture world, it usually a top-down design, have a whole picture and a split and go to different departments and then combine together. But usually for bottom-up, that we have a typical case is like children play a Lego game, and it plays one piece by piece, and it's bottom-up. So here is a model created. I hope it makes sense to you. So for top-down design, it always usually comes from the layout design or BOM structure design. So you have a clear picture on what the overall design will be. And so you need, the layout is in the center. And based on the layout design, you can extract some skeleton model. And then for each component, you need to define the reference geometry and the metadata, and for each component to use, to link. So for component 1, 2, 3, 4, any component, and they all associated with the layout. So for all these piece component, they just come up with a whole picture for the product. So that's the method for top-down design. So currently, we have 3 usually used top-down design approaches. It's approaches to achieve top-down design, right? So the first one is to new a part within assembly. So this is the most basic one, that you just new assembly, create import the skeleton model and the other new parts based on the reference on the skeleton models. And the second one is use Derive, that you create a new part and you derive a skeleton part model in your part. And the third one is our recommendation, is the sheet metal multi-body. You use the sheet metal multi-body and to create the context in one part, and then make components to make assembly. So go to details. So from the file structure, that usually for the first one, it's I only give examples for simple case. So you can imagine that how to use it in a big assembly. So assembly 1 and with a skeleton part in, and you create part 1, 2, 3, and by geometry reference on the skeleton part. And this one is assembly 2, and you have different parts, but each part is derived the skeleton part inside the part. And this is a multi-body workflow, and from the flow it looks complex than this one, but you can see this is the result, that by comparing the file management, it have one file less than other methods. So we go through them one by one. The first one is the parts with assembly. So for this part, this blue one is a skeleton model. And I create assembly, place it in, and create a new part, which is association with this skeleton model. So we can make a quick demo for this one. So I can hide the existing one. So I create assembly and place this skeleton part in. So then I create a new part, maybe part 2, and with this new template. So here is a tips. I guess maybe it's not new to everyone, that when you create a new part in assembly, it's recommended that you click the center point in the assembly to create this part. Then it will make each part, the coordinate system will be same in each part with the assembly. So now I create a sketch to project the top face for this model. Then I use face to create the first sheet metal feature. And now we will try, say, I want to create these flanges and look at that, how to make it associative. So I want to make this associative with the skeleton model, and I need to choose a tool geometry. But there's nothing to pick, right? So before that, you need to create a work point. Let's say the border. So a work point here is created. It's adaptive. So it's associative with the skeleton part. And now when I get back to the flange, I can choose this work point. So apply. And I can continue to create flange. And this time it's just a distance. And with flange, it's very easy to change the angle. And next, we will say why we say it's recommended to use the center point to be the center point of the part. And now I want to mirror these features in this side and in this side. For this model, that I can choose these 3 flanges, and to be mirrored with this. I can create it directly, and then again, I can pick this feature. Say I can mirror along this work plane and create another one. So it's easy to reuse your design in one part quickly. So I will show more about the flange, that about the wise extend functionality. So if I want to extend this flange, but with a wider vise, so how to make it? So by default, it's with vise extend method, it's based on edge. So how wide the edge is, that's how wide the flange will be. So we can choose vise from this dialog and say if it's auto-centered. So I can just say, oops, I can measure this length. It's too small. I'll pick it larger. Okay. And then this one will be bigger. Also, there are other options like offset. I can offset from this length as a 5 millimeter, and another as what? As 5 millimeter. So we can change to see the difference. So it's very flexible that for you to define the width for the flange. So also this options is used in contour flange and hem. So it's the same experience. Okay. And now we just do these steps. It's enough. So we go to the skeleton part. And show this sketch. And change the width to be 5 inch. Do update. Okay, I need to go back to this. So you see this part has been updated associatively with this skeleton model, right? Okay.
Good job.
Thank you, the neighbor. So let's talk about the advantage or disadvantage for this method. So we see that everything happens in one context. So I can refer the geometry info from the skeleton model by creating some mediums. So by creating some adaptive work plan, adaptive sketch, adaptive work points, right? So, but the disadvantage is that this adaptive stuff, maybe it's not so reliable. That when it's break, that you need to take some efforts to save the relationship back. And another bad thing is that when the assembly becomes complex, since this method requires you to always work in context with in-place editing status, you cannot just open a part to do the job. So this will bring some problems if the assembly becomes larger. Okay, so let's go to another one. This one would be better. That this one is use Derive. That derive the skeleton model inside of this part. So by mentioning Derive, that Derive have many different styles. Derive with surface or Derive with solid. So what's the difference? So by Derive with surface, that it's one surface body in this sheet metal part. And usually that you can use secant to make the sheet metal features quickly, since I can just directly secant this surface to be a new one. And another thing is that you can just do flat pattern in this part. So with currently the existing multi-body support in Inventor, that if there are multi-body in one part, that it's required to make parts for each solid and then to do flat pattern. So for surface Derive, that it don't need extra steps to do that. But the problem is that when you want to refer the geometry information that from the surface body, it's also required that you create some mediums that to connect them. So I will do a demo later after talking about the solids. So, but for solids, that you can derive this this skeleton model in the as solid in this part. The benefit is that for solid, and you can pick the vertex directly for the flange creation to connect these two geometry information together. And but for this workflow, that you need this to support. It's like you need to make part to make this solid to be a single part, and then to do flat pattern. Then this part will be associative with this part. So any changes from the skeleton model will go to this part and then go to this part. So it's quite stream forward. Okay? So let's see how it works. I need to run faster since the time is So this one is already created, so we can check the feature. See, each design in my side shares the same skeleton model. So when the skeleton model changes, I get a notification just to click the button to update the model. So for this side, okay. I derive this model as a surface. And the first step, I just secant this surface up. And for this, also I use secant. And I create bend to connect these two bodies together. And continue the flange. And others is the same. We can just use a mirror, same as the first model, to do it. So for surface derive, that often the most often used tools is the secant, and then you use blend to connect these two bodies together. And how about the solid one? Okay, get a notification. Same. So for solid, it could be very easy since I can just secant the first one as a new solid. And then when I do the flange, I can choose the vertex directly as the height extends definition. So I just choose this. I don't need to define actual geometries, actual work geometries to connect the relationship. Okay, so now that I need to do one step, make part. I make the solid 2 to be a part. And I can say I want to place it in assembly or not. This time I choose not. Then I create this part. And now I can create a flat pattern and to check the design. So that's the workflow from the multi-body to make part. Okay.
So is your thickness, is that linked to the original power plan?
Yes. Yes, the sheet metal rule is linked. So I will show you here.
So I think I got your question. So you mean the derived sheet metal part is sheet metal rule is linked to the source part, right?
Yeah.
So
is that new 2016?
yes. Yeah. Yes, 2016. So if you change the sheet metal settings in sheet metal rule, these changes can be synced to the derived sheet metal part. Yeah.
Yes. So look at this option here, that there's a link sheet metal style option. That it means that the default sheet metal rule will be transferred to the downstream. Yeah. Okay, come back. Oh, sorry.
How do you deal with multiple material thicknesses in a single?
Okay, it's a good question. That's yeah. It's something we are working in progress, and so we invite you to Beta Forum to do the validation for the new functionality. Yeah. Okay. So here comes a typical multi-body design, and for this design, it's from scratch. So from scratch means I don't need to prepare a separate skeleton model. This is just the skeleton model. It's a skeleton model for everyone. They self-reference each other. So it's created from the scratch, mostly for simple design. So for this air glasses, this cover is the first created, and for these two parts, it's created based on the first body. So there are 3 bodies in one part. So with this design, that similar workflow that you with multi-body in one part, and then you use make part. You can use make part to make each body to be a single part. Also, you can use make component and to make selected solids to be parts in your final assembly file. So that's the top-down design from scratch. Okay, let's see it. Okay, for this part, that from the file structure, we see there's a cover, there's a holder, and there's a support plate. So every solid is created in the same context. So they self-reference that the geometry information. So first, I create this this cover. Quickly go to this one. First, I create this body and with some geometry information. And then we go to create this face. Since there is a fixed length, fixed distance required that from the end face of this cover to this face, right? So we just reference this face to create a work plane to place the second solid. And the same situation for the third solid, and it starts from a face here, and then you can do flanges, and finally to make it. So with this 3 bodies solids in one part, that usually we will use make components, and we can choose also 3 solids in this design. Also, it depends on your needs, and you can just pick some of them. And go to next, and you can see here it also has a link sheet metal style option. I didn't check on color override, so it removes colors, but we can save the color back by check on the use color override from the source assembly, from the source part, sorry. So when we go to each part, that we can do flat pattern, that for each one. So during your design, you can make it at the very beginning, that when you get a basic shape for this solid, and you can make components or make part and to validate your flat pattern anytime you want to. So I need to quickly. So this one is the multi-body design from scratch, and the final one. This one is a sheet metal multi-body from skeleton model. So this is a method from the packing industry that usually you got a center material, and every covers is created based on the century solid. So you get the right size. When this century solid changes, that every covers in this part will be changed together. So in this example, there are five solids in one multi-body, and all created based on the skeleton solids.
You can import solids from SolidWorks or
Yeah.
other programs?
Yes.
Directly?
Yes. So, oh, I missed these tips. So, when you want to import maybe sheet metal design from SolidWorks or other competitors, that in Inventor we cannot recognize it's a sheet metal part directly. So there's one quick way to review it quickly. It's like we can import it in and use second to quickly review it, and use bend that I demoed a little bit on that.
So I have a question here. So you are talking about the multi-body or single body from third-party software
More assemblies,
assembly.
Yeah.
bringing in full assemblies, and then like we get machines from our customer, and then we have to skin them out. We have to do all the sheet metal parts that go around them. So we pull that in and we extract the geometry directly from them. In a lot of cases, like you said, they've created some sheet metal parts, and we've got to do both. We've got to do multi-part bodies and do our own parts.
Okay. So actually we can import single body, multi-body assembly from third-party software. So you can import the third-party data set into Inventor as externally or multi-body.
And then when they update, if they update during the design process, then I bring in their model again.
Well, yeah, you mentioned a cool functionality in Inventor. That it's not in the area for this class, but it's Inventor stuff at any CAD.
Yes.
Yeah. So you can do it. That import third-party model and keep association with the source file. Yeah. Okay. Okay. So this is the same workflow with the last one, with the one from scratch. And when you make the multi-body design in part, and you use make components or make parts to make them to be single sheet metal part and do flat pattern drawings in this workflow. So what's time? 15. So I think we don't need to demo this one either. Not either. We don't need to demo this one since many approaches I just demoed. So I have a skeleton model provided. So I think I can upload it in the AU class, and you can download it later to practice. Okay. So we mentioned many times on the new improvements in 2018. So I think that it's a good opportunity that to introduce Beta Forum to everyone, and you can join us to test the very earlier products in progress. So and then you can get a chance to provide feedback and join us with the design work. Okay, that's the objectives. Quickly, and go to tips. So don't go, they're gifts. So I prepared some questions. So I give you some minutes to look at it. And then, okay. So it's a gift time. So when I ask questions, and I said, I will say go, and then you can raise your hand and answer a question, okay? So the first one is, can we make a contour rule with a closed profile? Go. Oh, you're so quick. Oh, no? Oh, yes. Okay. Yeah. Okay. So.
Okay. So, small gift. So, button from taken from China.
Yeah.
Okay.
It's valuable since it's a gift from AU China. So it's you have double AU. The second one is which option do you need to check on when the cut is not normal to target faces? Go. Oh, okay. Cool. Okay. Thank you. So next time I say go, and then you raise your hand. Okay. The last one is which features are supported to create a punch iFeature? Okay, Evan. You can just talk some of them.
Extrude, revolve, sweep, fillet.
Cool. And the last one is cut. That's okay. I think I need to send more. Do you agree? Okay. So I pick another thing. Okay. So what's the first step that when you after you click convert to sheet metal? Okay. Here is faster.
Set your sheet metal default.
Nope.
Segment your face, the metal thickness.
Yeah, you are right.
Okay. And pick a face. Pick a base face to get the thickness. Yeah. Okay. Okay. So when the sheet metal fat pattern updates becomes slow, which option? I didn't say go. So which option you should check on? Go. Yeah. Yes. Cool. Okay. The last one. Very quick. Okay. So for flange, that when you want to create a flange to be parallel with a side face, that what you should do? Go. Back. Yeah. Cool. Okay. Thank you. Okay, that's all tips that you can review the slides later. That it's all online now. So I don't think we have more time for Q&A, but we can give some 15 minutes or 10 minutes to 10 minutes, and we have 5 minutes for Q&A, maybe.
Any question?
Yeah. All comments. Okay, then. Please.
One of our members, they were working with 16, and we sometimes send them step files for sheet metal. When they get a step file, can they convert it to sheet metal again?
You mean
Or step file is done with that?
you send a file from 2016 to 2014, and you.
Create a step file, SED, that can be imported into the ERP version.
And get sheet metal rules.
Sheet metal again.
Okay. Okay. Yeah, I think it's okay. People are hurry for keynotes. Okay. So for people who have questions, and you can stay here. And but for people will go, that remember that you can find us in the answer bar. It's just beside the exhibition hall, so it's easy to find us. Okay, thank you.